Imagine this. Right now, you're not just spinning with Earth or orbiting the Sun. You're being pulled towards something massive, something we cannot even see, moving at a staggering speed of 600 kilometers per second. Every galaxy, every star cluster around us, all of them are being dragged toward the same invisible region of space. But what is it? Where is this force coming from? Astronomers have been working for decades to solve this riddle. They calculated the location of this mysterious force, and they found something shocking. The largest gravitational anomaly in the local universe, one that is pulling everything in its path, sits right behind the one place in the sky we can't observe. It's hidden behind our own galaxy, the Milky Way. They told us gravity was understood. They told us we had mapped the universe's structure. But for 40 years, cosmologists have been measuring galaxy motions with precision using redshifts, peculiar velocities, and mathematical models. And what did they find? Every measurement pointed to the same location in the sky, the constellation Centaurus. This was dubbed the Great Attractor. But when astronomers pointed their telescopes at this exact location, they saw nothing. Not because there was nothing there, but because 20% of the sky is obscured by the Milky Way's dust and gas. The Great Attractor sits right behind this zone of avoidance where we simply can't see through. Now, if you've been following this channel, you know we like to track objects that break the models, like the mysterious 3I Atlas moving through our solar system. Its movement defies all our understanding of physics. Or the moon, which is locked in an orbit with such precision that no natural process could explain it. These anomalies are not random. They are evidence of something much deeper. And while we've been analyzing these peculiarities in our cosmic backyard, astronomers have been making even more profound discoveries on a galactic scale. It turns out the entire Milky Way is being dragged, but the explanations, they don't fit. We are dealing with mysteries that are not just strange, but revealing. This isn't just a cosmic oddity. It's evidence that our models of gravity and motion are incomplete, even at the largest scales. Make sure you're subscribed, because today we're diving into the data, the measurements, and the discoveries that challenge everything we know about the universe. And believe me, this is just the beginning. We are going to uncover not one, but three massive attractors, each one larger than the last. And each one forces us to ask a question that we might not be ready for. What if there's something beyond the edge of the observable universe pulling everything we can see? Let's start with a groundbreaking measurement. In the 1970s, astronomers were analyzing the cosmic microwave background, CMB, the afterglow of the Big Bang, the foundation of our understanding of the universe. The CMB is supposed to be uniform, a perfect isotropic radiation filling all of space with a temperature of 2.725 Kelvin. But there was a problem. When they looked closely, they found a temperature asymmetry. One side of the sky was warmer than the other just by a tiny amount, but it was significant enough to be measurable. And that's when the models began to break down. The CMB, supposed to be uniform, was showing a dipole, a gradient in temperature. One hemisphere of the sky was warmer, while the other was colder. So, what does this mean? It means the Milky Way isn't at rest. It's moving through space at a fast pace, about 600 kilometers per second, heading toward the constellation Centaurus. This motion creates a Doppler effect, compressing the CMB in the direction of motion and making it appear warmer. What we were seeing was not a flaw in the data, but concrete evidence that we're being pulled through space. But here's where it gets strange. Galaxies are not supposed to move like this. Space is expanding, meaning galaxies should be receding from each other, not converging. The Hubble flow pushes galaxies apart, but we are not moving away from the universe's expansion. We are being pulled towards something massive enough to overcome the expansion. And when astronomers tried to calculate how much mass that would require, they were shocked. The number was mind-boggling. 10 quintillion solar masses, 10 million billion suns. That mass should be visible. It should dominate the sky. But when they pointed their telescopes at Centaurus, they found nothing. The Great Attractor was hidden behind the zone of avoidance, a region we cannot observe with visible light. So astronomers turned to infrared wavelengths, which penetrate dust more effectively, and that's when they made their first breakthrough. In the 1990s, infrared surveys began mapping the forbidden zone. What they found was incredible. Hundreds of galaxies, previously invisible, were sitting right where the Great Attractor was thought to be. In 1996, René Kran-Kortog's team used X-ray data from the Rosat satellite, and the results were even more surprising. They discovered something massive. The Norma cluster, located 220 million light-years away, with a mass equivalent to 1 quadrillion suns. But even this was not the answer. The gravitational pull of the Norma cluster was not enough to account for the speed at which the Milky Way was moving. The numbers didn't add up. It could only explain about half of our velocity. The other half was still unaccounted for. This raised the critical question: was the mass calculation wrong, or was there something else pulling us that we hadn't discovered yet? Then, in 2001, a new survey called CISA mapped more of the zone of avoidance using X-ray astronomy. They discovered over 200 galaxy clusters, all previously unknown and all hidden for billions of years. When they added up the total mass in the Great Attractor region, they were left stunned. The mass was only 10% of what was needed to explain our velocity. That meant 90% of the force was coming from somewhere else. And so, astronomers started looking beyond the zone of avoidance. What they found was unexpected: the Shapley Supercluster. Discovered in the 1930s, but dismissed for decades, Shapley was thought to be too far away to influence local galaxy motions. But when astronomers finally ran the models, they realized how massive Shapley really was. It contains over 8,000 galaxies, concentrated in 25 galaxy clusters with a mass equivalent to 10,000 Milky Ways. And it's pulling everything. The entire Laniakea supercluster, 500 million light-years of space, is being dragged toward Shapley. Here's where things get really interesting. The Great Attractor isn't the source of this pull. It's just a waypoint. It's being pulled toward Shapley. For 40 years, astronomers thought they had found the anomaly. But in reality, they had discovered a symptom of something far bigger. The Great Attractor was only contributing 44% of the force. Shapley, a staggering 56%. This means the very object that had been the focus of cosmic research for 4 decades was not even the dominant force behind our motion. It was secondary. If they got that wrong, what else did they miss? Then, in 2016, René Kran-Kortog's team made another monumental discovery. While mapping the deepest regions of the zone of avoidance with the South African Large Telescope, they found another supercluster, even farther than Shapley. This was the Vela supercluster, located 800 million light-years away. When they measured its gravitational effect on local galaxy flows, it contributed at least 50 kilometers per second to our velocity. Now, astronomers had found 3 massive attractors, Norma, Shapley, and Vela, each one farther than the last, and this is where the pattern starts to become undeniable. With every new technological advancement, astronomers kept finding bigger structures, more sources of gravitational influence, which raises an uncomfortable question. How many more of these attractors are still hidden from us? Some astronomers began to wonder if the traditional view of attractors was wrong altogether? What if there is no source? What if the universe isn't being pulled toward a concentration of mass, but is instead flowing in one direction, like a river? This theory is called dark flow, and it suggests that the observable universe itself might be drifting not because of any single force, but because space itself is in motion. In 2008, Alexander Kashlinsky measured the motion of 1,400 galaxy clusters using the Sunyaev-Zeldovich effect. This effect occurs when CMB photons pass through hot galaxy clusters, giving them a directional energy boost if the cluster is moving. Kashlinsky mapped these energy kicks across the sky and discovered a coherent motion, hundreds of galaxy clusters all moving in the same direction towards Centaurus. The European Space Agency's Planck satellite disputed Kashlinsky's findings, claiming that their higher resolution data didn't show dark flow. However, Kashlinsky reanalyzed the Planck data and confirmed that the flow was still there, albeit processed differently. This debate is far from resolved, but if dark flow is real, it would mean that everything we know about cosmic structure is incomplete. If dark flow is influencing galaxies, it suggests that there are structures beyond the cosmic horizon, massive structures we can never see, because the light from them hasn't reached us yet. This would mean our entire understanding of the universe is based on incomplete data. We're only mapping 20% of a larger structure and calling it complete. And this is where things get even stranger. In 2017, astronomers discovered the dipole repeller, a region of space on the opposite side of the Great Attractor. It's a massive empty void, and galaxies are moving away from it, not because something is pushing them, but because it is empty. The galaxies were pulled out of it by the nearby attractors, making it appear like a repeller. But it's not pushing anything, it's just empty space. Here's the kicker. The dipole repeller and the Great Attractor line up perfectly. They sit on opposite sides of the Laniakea supercluster, as if the entire structure is being pulled by two forces. One is pulling, and the other is a void created by the previous pull. This means that the flow patterns we observe, the attractors, the repellers, they aren't random. They are part of a much larger structure that we don't fully understand. Laniakea, the supercluster that contains us, is part of something even larger. And that larger structure, the gravitational watershed, is not pulling us toward Shapley as we once thought. It's beyond that. Shapley is just another node. This raises an even bigger question. Is there a fourth attractor waiting to be discovered? Or is dark flow the key to understanding it all? We may never directly observe the forces beyond the cosmic horizon, but we can keep searching, keep mapping the sky, and keep pushing the boundaries of our understanding. What do you think? Drop your thoughts in the comments. Is it a fourth attractor, or is it dark flow, something beyond the observable universe? And remember, 20% of the sky is still hidden. Make sure to subscribe, because when the James Webb Space Telescope and next-generation X-ray telescopes map the hidden regions, we'll be right here, tracking every discovery